Hello, everybody. Adam Lusick here, and today we're going to talk about fine-tuning OpenAI models. I'm going to go over a little bit about what fine-tuning is, how it works, why I decided and started fine-tuning models, and then also all the steps that I took to go from taking my data set to fine-tuning an instance of GPT 3.5 Turbo onto it. So to give a brief overview of where fine-tuning kind of comes into play in the life of a language model, I found this really good simplified graphic that breaks it down pretty simply. So to go through this real quick, the base language model, or what they kind of call the foundational model, things like GPT 3.5 Turbo, GPT-4, GPT-4 Turbo, they're all pre-trained and all of their weights and biases internally are calculated via this massive data set of text. OpenAI takes things like web crawl, wikis like Wikipedia, and hundreds of books, extracts the text, and then runs it through all of their proprietary fun stuff to make the base foundational model. However, you might realize then that that means that the inference that you're running on your base model is very broad and generic. So what you can actually do is introduce fine-tuning, which is pretty much taking your own data set of your own specific things that you want the foundational model to be better at either reproducing or better at creating content more similar to it, and then partially retraining the model on that data. That then gives you a fine-tuned language model that you can do query response flows like this, or just run regular inference on, and should give you better results for what you're looking for in your own specific data set. OpenAI's documentation on fine-tuning reiterates a lot of these points that we were just talking about. They also claim that fine-tuning can help with, higher quality results than just prompting. Also things like the ability to train on more examples than you can fit into a prompt window. They elaborate on that second point by saying, fine-tuning improves on few-shot learning by training on many more examples than can fit in the prompt, letting you achieve better results on a wide number of tasks. Once a model has been fine-tuned, you won't need to provide as many examples into the prompt, thus saving things like costs and enabling lower latency responses since you won't have to provide as much context if you actually fine-tune on a specific dataset. They do provide a warning about actually going through the process of fine-tuning, which I completely agree with. And that's basically that fine-tuning is pretty resource intensive and time intensive. They recommend first that attempting to get good results from the language model with prompt engineering tactics, prompt chaining with things like LangChain, function calling, and the reasoning behind that is that there's a lot of tasks which the models might not initially appear to perform well, but with the right prompts and with the right tuned prompts, not the tuned model, that can actually be mitigated a lot. Additionally, it's a lot quicker to iterate over prompts and other different tactics using prompts and getting much faster feedback than going through and creating data sets and running training jobs. However, if you are still looking for fine-tuning, some of the common use cases that they provide are setting the style, tone, format, or other qualitative aspects of the generated output, improving its reliability at producing a desired output, correcting failures to follow complex prompts, handling different edge cases in super specific ways, or performing a new skill or task that's hard to articulate in a prompt. And then one thing that they put here that I really like is a high-level way of summarizing this and putting it succinctly is that fine-tuning is really best when it's easier to show, not tell a language model. Showing being just, running it through your data and its desired output, not telling it by prompting. So to go over a little bit about what I use fine-tuning for, I found that fine-tuning is really, really helpful for complex classification tasks. It can really help getting more consistent and correct output for labeling or generating different labels for data sets. And a couple examples that I've written down here, it can help with getting more accurate readings for things like binary sentiment classification, labeling, let's say, like a social media comment as negative, neutral, or positive, different intent classification, labeling what something may be used for. It's also could be better for things like hierarchical classifications where you have multiple labels that are nested within each other and you want to get the correct line of something. Like let's say a web page that you're trying to tag in Adobe Experience Manager might be under science, then biology, then genetics. You don't just want to label it as genetics. Additionally, things that are like multi-label text categorizations can be a little bit difficult for these language models. Something like the discussion on the implications of economic policy could be considered as both political and economic, and you would want to sort of extract both of those labels as well. So to actually pick a topic and pick some data to fine-tune a model on, I wanted to choose a pretty complex task, and I think I found a good one. So we'll be going over the Go emotions dataset for the task of multi-label classification of text and emotions. So what we'll be asking the language model to do is look at sample text, and then from that text, provide one of 27 emotions or multiple emotions to it. And I think this is a great example because of a few reasons. The first is that some texts can have more than one actual emotion. You can see here in this diagram and table from the paper of this data set, this text here has two labels, gratitude and approval, whereas, some of them only have one, confusion. I also think that this is a good example because labeling things with emotion can be very subjective. It's difficult even for humans to understand emotion a lot of the times, so especially language models won't be great at actually being able to do a labeling task like this. Additionally, because there are 27 emotion categories, it would be a little bit ridiculous to try and craft some specific prompt that has examples of all 27 emotions with examples of multiple labels on single text inputs to actually do this. So what instead we're going to be doing is fine-tuning an instance of GPT 3.5 Turbo on a portion of this data set to try and recreate better output for the actual labels given the input text. Jumping back to the OpenAI documentation real quick, we can see that the format that we actually need to transform this data set into is going to be as such. So it's going to be in a JSON lines file with a dictionary that reads messages, has the system prompt with the content here, and then it's going to have the user input here, and then finally the assistant content output. So we're going to go through now and show you how I loaded this data set and how I actually formatted it all to look like this. So to start that, half the reason why I chose the Go Emotions dataset is because it's also available on Hugging Face. And Hugging Face makes it super easy with their datasets Python library to deal with super large datasets like this one. See, it has 265,488 rows. All of these things with the text, and then we can see here some of the actual emotions that we'll be going over. But they make it super simple using just a simple couple lines of importing the package, and then just with this, you can actually download the data sets. So jumping over to the Jupyter Notebook, that is exactly what I did. I imported pandas as well because I just enjoy working with data frames a little bit more than the actual specific datasets package from Hugging Face. I just know it a little bit better, and so that's what I've been using. But we can load that super simply with just load dataset Go emotions, and then it'll do all of the downloading here, and you're ready to go and get started with it. Looking at the first line of the data here, we see that it returns a dictionary with the text of the comment and then a specific label which maps to a specific emotion and then a unique identifier. I pretty much just wanted to use the text and the emotion because it makes it super simple to work with. So I created a quick label index that goes all the way from 0 to 27, gathering all 28 different emotions that are labeled here. Things like anger, annoyance, grief, joy, love, surprise, sadness, neutral, everything in between. And then what I do is for the range of the first 1,000 comments, I go from 0, which is the first starting from 0, all the way up to 1,000, grab the text of the comment, grab the label of the comment, and then from the label, I map it with this quick index, pop it all into a pandas data frame that looks like this. So on the left, I have the comment, and then on the right, I have the emotion label. And in some cases, multiple labels here. One thing to keep in mind is that all of these comments are from Reddit, so there's going to be a little bit of profanity and a little bit of, uncouth activity, as is on par for Reddit communities. But just to give it a quick check, in the first 1,000, I put together a simple script that will just count all of the emotions to make sure that I have all of them present at least once so that we can get a very holistic view of the emotions. And for creating our both training and validation data set, it will have enough examples in there of multiple things. So running this, we see that we've got at least one, just one pride here of everything in the first 1,000 entries. So we can continue to actually use just the first 1,000 to create our couple data sets that we're going to need for fine tuning. But of course, we need something to compare our fine-tuned model to. So I put together a quick script here with LangChain to run GPT-4 Turbo over the first 100 entries in this data set to see its output. And so this is just following a pretty traditional LangChain common expression language flow using a string output parser, just chat prompt templates and a chain here with some runnable pass-throughs of the comment that's actually going to be put through there. And then a list of emotions, which I just take the label index that I have and convert it to a list and insert it there. To go over the prompt that we're going to be using real quick, I say, you are a cutting-edge emotion analysis classification assistant. You analyze a comment and apply one or more emotion labels to it. The emotion labels are detailed here, and then in brackets, this is where the list will be plugged into. Your output should simply be just the respective emotion, and if there are multiple, separated with commas. Then the comment is here, in brackets again, which will be inserted with a runnable pass-through. Then it's just what I said. I create the input data of the comment and emotions with a quick function here that will take both of those input, run it through the chain, and then return the output, which we do that for the first 100 entries in this data range, and then append it to the data frame. So looking at that, we can see that GPT-4 Turbo is actually a lot more verbose, I would say, than the regular emotion label that the Go Emotions dataset originally has. Something like this comment, to make her feel threatened, has the emotion label of just fear from the dataset, but GPT-4 Turbo is saying it's both disapproval, anger, and fear. Depends really on what you're looking for with this output here. I would say that the GPT-4 Turbo output is pretty good. However, if you're looking for something specific, it's not as, not as simple, not following exactly what this expected emotion label might be. Something like, your aunt has some damn nerve, though, has anger, annoyance, and disapproval, but it's labeled as neutral here from the dataset. I would say this is more neutral because obviously they're not angry, annoyed, or necessarily even disapproving from this comment. It must just be some simple neutral observation. And so now that we have a baseline, it's time to create both the training and the validation dataset in JSON lines format. And there's no difference in the actual formatting of the training and validation data. You just need both because you'll have one to actually train and fine-tune the model, and then one to compare against and validate the data. This is very classic, just machine learning, neural network training stuff that you use to actually do this stuff. So if you're interested in learning more about that, perchance I could do a follow-up. However, simply put, we just need to make one training data set and then one validation data set. So to do that, I'm actually going over rows 100 to 700 and pulling all of those comments out using the initial 1,000 that we're using, but excluding the first 100, which will be our baseline comparison that we're using up here. And then it's just simply put in the same format that we see here in the example format from OpenAI. I just did a little bit of indenting to make this actually a little bit easier to read. I take the same prompt, I input the actual list that is generated in here, and then we've got the user. I have an F string so that we can input a comment, and then another F string here in the assistant output so that we can insert get the output of the emotion label. And then what I actually do is use a little bit of this, of opening up the JSON lines format, dumping it all in there. And then since it's a JSON lines and not a traditional JSON, what we're doing is not indenting, but getting a new line at the end since it'll be delineated with line breaks. Same for the validation data, except instead of going through rows 100 to 700, we're going from 700 to 1000. So we're going to be using 600 entries for the training and 300 entries for the validation data. Once those are run, this is what it looks like. Exactly what we'd expect with everything being on one line. We can see that this is the system prompt here, followed then by the user prompt, which is analyze the emotion of this comment, and then I insert the comment, and then the output is the label from the data set. And so it goes through and creates this. We have 600 entries here, and then also in the validation data set, the other 300 that we're using. So all the way up to 300. Great. So now that we have these, what we can actually do is then verify that they'll be good and ready for fine tuning. And OpenAI links actually from their documentation to this wonderful cookbook that they've got here that is Data Preparation and Analysis for Chat Model Fine Tuning from Michael Wu and Simone Fishman. So they go into more depth of to what each individual thing is doing here, but I pretty much just took all of this code one-to-one and then popped it into a Jupyter notebook here that I'm using. So what this pretty much does initially is it prints out the number of examples and the first example. So we're seeing successfully that when we path over to this training document, we have 600 examples. That's exactly what I want. And then we can see what the first one looks like. The second chunk here is actually looking for formatting errors, making sure that you're not misspelling anything, making sure that you're not putting anything in weird areas. We see here that there were no errors found. The third chunk then is going to be encoding so that we can get a look at the tokens and actually see what the token count is going to be. So after running it through a few things here, we see that there was also no missed system messages, no missed user messages. We're seeing 3, which is exactly the number of messages per example that we're looking at. And then we can see the distribution of the number of tokens per example. We're seeing that there's a minimum of 193 tokens, a maximum of 232 tokens, with a median of about 207 tokens per. We're also seeing that there's not a lot of assistant tokens per example. We're not really using that at all. And then since we're using a specific instance of GPT 3.5 Turbo, the one thing that I changed is the actual token limit. So we're not running into this at all, given that our max number of tokens is actually just 232. But for each example, they do have a token limit of 16,385. And it checks for that. So we see that 0 examples may be over 16,385 token limit. So that's all good. Then what it'll do is calculate some initial pricing and epoch estimations. And so epochs are basically the amount of times that it will go through each individual entry on your data set to train the model. So how many times it'll iterate through the data set. And by default, OpenAI tends to do 3 epochs. And then it estimates that it will do 3 epochs across roughly 124,416 tokens, which will be charged for about 373,248 tokens. As for what pricing looks like on that, so we can estimate the pricing. For training an instance of GPT 3.5 Turbo, it is about $8 per 1 million tokens. And if you do a little bit of math, then that is an estimated $2.99 about for training this model. To validate that a little bit, we can see that the actual model, and we'll go into more of this in just a second, came out to about 369,648 tokens trained on 3 epochs, and the total cost of it was roughly $3. So pretty accurate, down to give or take about 5 cents. To actually fine-tune the model, OpenAI makes it super easy once you're actually in their API platform here. All you got to do is click on Create, select your base model. For this one, we'll be using GPT 3.5 Turbo 0125. That is the best model that you can use without actually just hard coding in. And so you do that. You upload the training data, you upload the validation data, and then you add in a custom suffix here. So for mine, I just put in Go Emotions. And once you click start on that, it'll pop up here in your fine tuning tab, and then this UI will also appear. So let's go through what all the things here mean. So job ID is just the unique identifier for the current fine tuning job. Suffix is what you entered when you were in that create menu. Base model also is what you entered in the create menu. Created at is the timestamp of when you created it. We went over what train tokens and epochs are. You have the links to your training and validation files if you so care to look at them again. And then down here is the more technical stuff with the training loss, validation loss, different messages about the job, and the metrics. So to go over what this loss actually means, the loss during the training is a measure of how well the model is actually performing given the expected outcome. And so what we're seeing here is a very low training loss, which means that given the training data, it's performing very well, which has a few fallbacks. What we're probably seeing here is a little bit of overfitting of the actual model to the training data. This is completely expected, as what we did was only input about 600 entries into the actual training data, whereas normally models of this size iterate over millions and millions of tuples. The validation loss is a little bit more telling then, and we see it's at 1.8085, which is much higher than the 0.0001 of the training loss, and that's how well the model is performing on new data that it's being validated with the validation data set. And you can see, given across all of the steps here, which we can look at in the metrics, what this validation training data loss is likely to be. And the reason it's not super consistent is for a few reasons. The first is that we're only training this over 3 epochs, so only going over the data 3 times, and we're also only partially retraining the model. So generally, when you're partially retraining the model, you do that in different batches of the actual data. So it'll go through and look at different parts and adjust different weights at each step of the way. So that's why for something this small, on such a small scale like this, you're not going to necessarily see a very consistent line here with either training loss or validation loss. But you can see that at some points the training and validation loss was higher and lower than others. However, as for the time that it actually took, I created this job at about 6:38 p.m. and it actually started really fast, about a minute later, and then it took roughly 1 hour and 30 minutes for this entire job to be completed. To give another example, I have this other model that I fine-tuned a while ago, and it was only 100 lines of data and 10 for the validation, so certainly not anything, super in-depth, but it took a couple hours. There was about 2 hours before the job actually started, but then once the job started, it only took about 10 minutes for everything to be fully done. But once that is all done, you can start using your model with this string right here. So that's what you're going to be specifying to and leading to when you're actually doing the program. And let's get into that and check out the results now. So what I did here at the end of this notebook is I just put together 2 of the exact same script that I used with GPT-4 Turbo to give us another output with the baseline GPT 3.5 Turbo, and then again here with that custom suffix of our fine-tuned model. And then just to give a little sneak peek of what that looks like, it output it all to an Excel file, which I then uploaded to Google Docs. So let's check out how these actually performed. So just to set this data up, we've got the comment here, the first 100 of that 1,000 lines that we were working with, the emotion label here from the Go Emotions dataset. So this is what we are expecting or trying to get close to. And then here we have baseline GPT-4 Turbo, baseline GPT 3.5 Turbo, and then our fine-tuned model. Just to give some sweeping overviews, what I also did is I did some conditional formatting. So if it is not equal to this emotion label that we're expecting from the Go Emotions dataset, it will fill in with red. And if it is equal, it will fill in with green. So just looking over these real quickly, we can actually see that there was about 3 of the same outputs from GPT-4 Turbo, 16 of the same, funnily enough, from the base 3.5 Turbo, and then, as is expected, our fine-tuned instance of 3.5 Turbo had 47 of the 100 outputs, very similar to what we were expecting with the Go Emotions label. So not exactly 100%, but pretty accurate, especially in comparison if what you're looking for is this output in comparison to baseline 3.5 Turbo and baseline 4 Turbo. A few of the notes that I have down here is that sometimes it'll just get half the labels. So the Go Emotions dataset labels this comment, "Oh, she'll probably come around," etc., as amusement and approval. And our fine-tuned model just put that it was amusement. Something here that I actually noticed is that for this stupidly stubborn / stubbornly stupid, it was labeled as anger from the Go Emotions dataset, but then our fine-tuned model labeled it as likely more neutral. And I would actually agree that it is probably more of a neutral comment than not, given that it's from Reddit. Some of the things here, I also noticed that this, "Your aunt has some damn nerve though," was labeled as neutral, and our fine-tuned model said that it was anger. So likely not anger. I would say more so along the lines of neutral. One of the other things, just to make a note, is that this says gratitude and love. This says love and gratitude, so it is the same. So I put a note here that it is the same. But overall, we're seeing that our fine-tuned model is much more in line with our expected outcome from our labeled data set that we're seeing here. So I'm really pleased with this output, and we're seeing some really decent stuff, especially some improvements going from the unfine-tuned model to the fine-tuned model in terms of our expected output. With that being said, all of the output, all of the notebooks that I used, and all of the resources that I have are going to be down in the description below. So I hope this was super informative. If you have any questions, feel free to comment them, drop a like, hit a subscribe, all that fun stuff, and hope this was useful for y'all. Thanks for watching.